All right, let's take a deeper look at the assembly process. So here we're going to look at each element, and of course each one can have its own A sub I, L sub I. We've gone over this before. Each element is subjected to a traction force. It has a unit per unit length. It has a body force per unit volume. It has its own Young's modulus, and a concentrated load is applied at node 2. Okay. Here, we're actually assuming that E and F are constant throughout. So each element has its own stiffness matrix. Okay, so we can have a superscript I there that corresponds to those corresponding cross-sectional areas and lengths. We have the element connectivity here that note in the future we get more tricky, so we'll mix this up. So there's no reason we have to have node numbering 1, 2, 3, and 4. We could have 1, say 3, 2. That node numbering, where you place it, is arbitrary. I know that adds another level of complexity that we'll talk about later. The element stiffness matrices can be expanded using the connectivity table and then summed. All right, so let's write each one. So here's the first element. Here we're using 1, 2, 3, 4, 5. So this is the same number of nodes. It's a 5 by 5. And element 1, which values does it have? Well, it has values 1 and 2, right? 1 and 2. It turns out that 1 and 2 are the same as the local numbering, right? So the local numbering is 1 and 2. Global numbering is also 1 and 2. So those go in the 1 and 2 positions. All right, so pretty clear. Let's now look at element 2. Element 2 has nodes 2 and 3. So we went over this before. So 1, 2, 3. What is the numbering locally? Well, this is B. 2 would correspond to 1, right? And 3 will correspond to 2. How do we know that? Well, we actually have it specified up here. So element 2, the local node 1 is 2, and local node 2 is 3. Okay? So locally we're here 1 and 2, 1 and 2, which correspond to 2 and 3, 2 and 3. So we put that 2 and 3 in this position. Same way with the node 3, we already kind of went through that one. That involves 3 and 4. And finally, element 4 corresponds to nodes 4 and 5. So 4 would be locally would be 1, and 5 locally would be 2. And globally, we put it down here in the global stiffness matrix corresponding to 4 and 5 positions. And these are just sums. So you see the plus sign there? And so when you add it all up, you get something like this. And so this is a great example of a banded matrix. And add that up, and here is the global stiffness matrix. Notice that since E was constant, we pulled that out. Also notice that you have some terms in the global matrix that have contributions from multiple elements. Pretty interesting. The other thing you notice is that it's symmetric. So you notice that these values off the diagonals are symmetric. And you also notice that it's filled with lots of zeros. So this is an example here of a band. Okay, you see, it's on a C off the diagonal, a band that you could represent. You don't have to represent this whole entire thing filled with lots of zeros. The global load vector is assembled in the same way. Here we're going to have the F. So for this term, for example, we're going to have locally, this is going to be 1 and 2. 1 and 2 for element 1, which corresponds globally to 1 and 2. So we put, this is a sub 1, L sub 1. We put A sub 1, L sub 1, F, and you see that down here too, in the 2 position. Okay? So this term is basically from element 1. And then for element 2, let's do element 2 is 2 and 3. So it's A sub 2, L sub 2. So that's going to be here. Okay, the global load vector is assembled in a similar way. Here we're going to have values of both tractions and forces. So elemental values, Fe, T sub E, look like this. We derived this before. So if we substitute our values in here, let's look at element 1. So element 1, again, we have local connectivity 1 and 2, which also correspond to the global numbers 1 and 2. And so we're actually going to have these values at those nodes. Okay, so here we're representing A1, L1, and then we have an L1, T1 over 2, and that corresponds to node 1, and then node 2 will also have that same term. Okay, so that gets applied to nodes 1 and 2. Now if we go look at, so that was for element 1, if we look at element 2, it also incorporates global node 2, right? So locally that would be 1, but globally that corresponds to 2, whereas local node 2 corresponds to global node 3, right? And so what we're going to do is put that value in here. This is for element 2. So we have the values here for element 2 and also here. And so because they have shared nodes, we get that kind of staggered effect all the way down. Now element 2 also has a node with a point force on it. That is, node 2 globally has P2 applied to it. So that gets applied in that row. No other nodes have that applied load there. This is how we fill in that matrix in a similar kind of way. So let's take a little break now and talk about the properties of K, and we'll also follow up with another example.